Any questions about anything from last time? Or about anything? Yeah.
I guess we skipped the section of the book of polynomials.
Yeah, I thought you. So 3.1 is something I would just expect you to read, because it's. You should be familiar with all those words, I think.
Yeah.
Read 3.1. It's kind of an easy thing to read.
We can't see that.
Sorry. But I will talk about it as I need it, but I didn't want to blow a whole lecture talking about standard words that you know from somewhere else. But I would expect you to read that section carefully.
And 3.2 also.
3.2 I have talked about. It's the complex, it's log and exponential. So let's see. I'm going to talk more about the complex log today. Last time I told you the principal branch. There's the mapping property of it, and the principal branch was such that when you take the principal branch of a log of w, then the real part is determined. It's always the same, but it's the next part, which is the argument of w, that requires a choice to make. And you take the argument in the principal branch. So remember, I like to write arg w as a set. So theta is in an argument. But in the principal branch, you take the theta between minus pi, and when you're on the when you're on pi, you let the theta equal pi ren instead of theta equal minus pi. But we'll be thinking of this as a mapping on an open set, and so we won't care about that, the red lines where there's a tug of war about what the argument is there. Question?
The capital L log is principal log, right?
Principal log, yeah, that's my convention. I think the book follows that convention too, that a capital L is the principal branch. And last time I mentioned other branches, and I use this notation that if I let my angle go from let's say I alpha, let's see, this is the I alpha horizontal line, up to I alpha plus 2 pi. So that's an angle with range 2 pi. And we get a similar picture which I described last time. Instead of having the branch cut going out the negative real axis in this case, e to the z goes this way, and this branch cut now would be sailing out angle alpha. So if this is the real axis here, and this angle would be angle alpha. And the e to the z would map this 1-to-1, the shaded region, 1-to-1 onto like that. And I like to call this branch, I like to use a script L here, log sub alpha of w. That's a branch. And that it's exactly the same as principal branch, except we don't care what happens when there's a tug of war. And we write log alpha of w. Real part's got to be log mod w. But then we take an argument here that goes from alpha to alpha plus 2 pi. So alpha would be less than that, theta is less than alpha plus 2 pi. And we won't care what happens on the red lines. But let's see, in the homework, you're going to be thinking about the Cauchy-Riemann equations in polar form. And this is a primary example where that would be handy. So in polar form, you would write f of r e to the I theta in a polar rectangle would be equal to u capital. I'll use capital U's and V's for my polar coordinates. That would be the notation in polar form. And then the Cauchy-Riemann equations, kind of like red box number 1 and red box number 2. If U and V are C1 smooth, on a polar rectangle, let's see, what's a polar rectangle? That would be a set of r theta such that r1 is less than r is less than r2. Let's see. We don't want we don't want 0 to be the origin to be in a polar rectangle. And theta would be less than between 2 alpha and beta.
Why is the theta between R1 and R2? Or is it supposed to be R?
That's dumb, yeah. I meant R. So I suppose I got two C1 smooth functions like that, and they satisfy the polar Cauchy-Riemann equations, which are du dr needs to be equal to 1 over r dv by d theta, and dv dr equals minus 1 over r du d theta. Those are the polar Cauchy-Riemann equations. If they satisfy that, then F is analytic in the polar rectangle. In the polar rectangle. Okay, that's the fact. I'm going to show you multiple ways of showing this. You're going to think about it in the homework a little bit. But before I do that, let me give you an example. Let's see, the log alpha of W is equal to, let's write it like this. This is what I've been writing. Or I could write log alpha of r e to the I theta equals natural log of r plus I theta. Okay, so this is the capital U and this is the capital V. And in the polar rectangle, we'd have here r bigger than 0 and theta between alpha and alpha plus 2 pi. That's the polar rectangle we're talking about. And of course, you can check that the Cauchy-Riemann equations hold. They're simple to check. And you also need to check that U and V are C1 smooth. In fact, they're C infinity smooth. So check. So that means that the complex log function is analytic. And so all those branches I talked about, they involve some alpha. Okay, so before I continue here, now that I know that it's analytic, let's find its derivative. Let's find d by dz of any old branch. This is true for all branches. So I'll put the alpha in there to emphasize that it's any old branch. Well, let's see. I got to think a little bit before I do this. You're used to the real version of exponential and log. And I'll call this number 1. This is an always true thing. The complex exponential of the log, of any old branch of log, is always z. This one's always true. Because that's how we cooked up the log. It's supposed to be the thing in those maps that when you put it in e to the e, you get z. So this is true just by the way we cooked it up. The one that's not always true, that you would expect to be true, if you were to take the log of the exponential, you might think, oh, this one's going to spit out e to the z. This one's dangerous. Careful. Sometimes it is, sometimes it isn't. But what's guaranteed is that this would be close to z. You might need some multiple of 2 pi I here. You would need the right angle to stick in there to make it for some n and z. Integer. Okay, so that one's not always true. But number 1 is always true, and that's the one I'm going to differentiate to figure out what the derivative of the log is.
That not always being true, is it that there isn't always a n that satisfies the equality? Or
There might be an n there, but you would expect to get z. You might need to add some multiple of 2 pi n.
Right. So
I.
That equality will always holds for some.
For some n.
Okay.
Yeah, but if you in the real case, the log of e to the z would be z. If there was a real number, and that'd be guaranteed because it has there's a unique log function that's the inverse. Here we have to make choices, and the choices show up there. I guess I should check why 1 is always true. Let's check 1. E to the log alpha z, that would be e to the natural log mod z plus an I alpha, where I alpha is an argument. And so that would be z times e to the I alpha is an argument for z. So of course that's z. Theta is an argument for z. Okay. Well, I can differentiate number 1 using the chain rule. It's an easy thing to do, kind of like you do in freshman calculus, actually. let's see, we have z is e to the log alpha of z. So when I differentiate d by d, when I take derivative with respect to z, on the left I'd get a big fat 1 because d by dz of z is 1. And in the right I would get, let me write it like this. I told you I'd never do this again, but I'm going to write e of log alpha of z. So when I differentiate that using the chain rule, that would give me e prime of log alpha of z times d by dz of log alpha of z. And e prime is itself. So that is going to be e of log alpha of z times d by dz of log alpha of z. And that's the one that's always z. And so now I can solve for that derivative, and I get d by dz for any old branch of log is 1 over z. Put that in red box. Just like in freshman calculus. Except now we have multiple branches. Let's see, as long as I'm talking about logs here for a second. Some rules are absolutely go over and some rules don't. Here's a rule that there's a problem with. Warning. You might ask, is the log of z1 times z2 equal to the log of z1 plus 2, z1 plus log? It'd be nice if it were. Unfortunately, maybe not. For example, if I was using the principal branch and those z... let's see, what's an example? Here's... I'm going to use the principal branch. So my branch cut is over here. Let's see, if my Z1 and Z2s are both in the first quadrant, I'd be safe. So why don't I have a, well, I have a Z1, I'll have a Z1 here. And how about a Z2 over here? I'll make the Z2 pretty close to the pi angle. When I multiply those two, they go past the cut. Let me see. I'm going to make this Z1 just big enough so it would push it over. Okay, Z1, Z2 would be over here somewhere. And the argument would be a negative number. and these two arguments would both be positive. So what we see from this thing is that the argument of Z1, Z2, actually the principal argument, would be less than 0. But these arguments, Zj, would be greater than 0 for j equal 1, 2. So there's no way that they would add up like that. And if you think harder about it, a true thing would be, so here's a true fact. Log alpha of Z1, Z2 is equal to log alpha of z1 plus log alpha of z2 plus, perhaps, some multiple of 2 pi. Some n and z. That's a true fact. In the book, you might notice the book writes something down, and here's what the book means. So the book, the book writes, this is my set notation, z1, z2. This is a true thing. This is as sets. So important to mention here, as sets. When you use the notation that log represents a set of numbers, all the possible things, so that e to it is z1 plus z2, that first one. So here's a fact that that's true. Okay. Here's a fact that's true. Principal branch of z1 times z2 equals principal branch of log z1 plus principal branch of log z2 when z1 and z2 are in the first quadrant. Because then you can't make the angle go past the cut, and you're safe. Anyway, my warning here, we don't have to think too hard about this, but if you think you can just go ahead and use facts you know about log from real version, you might be mistaken. Let's see, I'm going to go back to the polar Cauchy-Riemann equations now. The book gave you a hint on how to do it, and I'm not sure that's the best way to do it. So back to the polar Cauchy-Riemann equations. Okay, we've got two ways to write an analytic function now. The way we started out writing it in terms of a little uxy and a little vxy. And we got the regular old Cauchy-Riemann equations, the rectangular version. And now we're going to write it in a new way. F of r e to the I theta equals capital U of r theta plus I capital V of r theta. Okay, and if you start thinking about what this means, it means that U of r theta would be the same as U, let's see, in that case, at the polar point r theta, x would be r cosine theta. And y would be r sine theta. Okay. And v of r theta would be little v of r cosine theta, r sine theta. Okay. And so now if so I'm going to use the R2 to R2 version of the chain rule. Let's see. du dr would be equal to du dx cosine theta. That's the d by dr of r cosine theta. Plus du dy, d by dr of the second thing would be sine theta. Okay, that's the chain rule. And the u of du d theta would be du dx minus r sine theta plus du dy r cosine theta. Okay, I want to simplify this, and so I want a 1 over r here instead. Then it would look like there's a nice, if I divide by 1 over r here, I'd get 1 over r du d theta equals something very similar to that first line, namely du dx times minus sine of x, minus sine of theta, plus du dy times cosine theta. Okay, and you write out exactly the same thing for the v ones. Similar for the v's. Very similar. It's just there's v's where the u's are. And here's when you write that out, you're going to get this. Star. Du dr, dv dr, and 1 over r du d theta, and 1 over r dv d theta. You write that out and you get a matrix equation. Cosine theta, sine theta, and minus sine of theta, cosine theta, times du dx, du dy, du dx, dv dx, du dy, dv dy. And now you look at this for a second and realize there's something funny going around here. The Cartesian CR equations would mean this matrix looks like A, B, minus B. And the polar Cauchy-Riemann equations would mean that this matrix looks like alpha, alpha, beta, minus beta. And this thing is the same kind of thing. A, B, minus B. Okay, and it's a fact, an easy fact is that when you multiply two matrices of that form together, you get the same kind of matrix. So an easy fact. The product of two of those matrices, of these kind of matrices, product of matrices in this form is in this form. You just check it. Do it, and sure enough, it sure is. Okay, so what does that mean? That means if we know the polar, what does it mean? No, it means if we know the Cartesian, then we also know the polar. Cartesian Cauchy-Riemann equations imply the polar ones. And we want to go the other way too, an if and only if thing. And so if I were going to go the other way, I'd multiply by the inverse of that theta matrix. So I'm thinking now, Or was that cosine theta? Cosine theta. What was the matrix? Minus sine theta, sine theta. That's a rotation. The inverse of that matrix would be 1 over the determinant. That's cosine squared plus sine squared, which is 1. And then remember, I think I've done this in here, haven't I? The inverse of a 2 by 2 matrix. You swap the diagonal elements when you take an inverse. So you interchange these, and then you put minuses in the other spots. And the minus here would be sine of theta and minus sine of theta. So these are minuses. So what am I doing here? I'm doing this fact. A, B, C, D inverse is 1 over the determinant, AD minus BC, times the matrix. You swap the diagonal entries, and you put minuses in the other spot. So the inverse of that matrix is the same form. And that means I can put it on the other side. I can multiply this matrix equation on both sides by the inverse of that theta matrix, and then I'd see the other direction. Question?
What if doesn't AD minus BC mean that we should have cosine squared minus sine squared?
Minus a minus, which is a plus. Yeah, there's a minus sign in one. There's a minus sign in one of those. So when I minus a minus, I get a plus sine squared. So the determinant of that thing is 1. And so we see the inverses of the same form. Inverse of the theta matrix is same form. And so I can multiply through by it on the left and see that I might be getting carried away with this. Multiply on left by the inverse. And then we see, by this easy fact, what did I prove before? This would show that polar Cauchy-Riemann equations imply the Cartesian ones. So they're 100%. They're 100% equivalent. Okay, that's a perfectly good way to demonstrate that. Kind of long and involved. What the book was suggesting you do in that homework problem, or start from scratch. Start from first principles like we did. When we did the Cauchy-Riemann equations the first time. Remember the Cartesian ones. Blast. Cartesian. We did the Cauchy-Riemann equations by differentiating along the horizontal and along the vertical. And we let a difference quotient slide in 2 different ways. Okay, in the polar form, another way to do it would be we'd have a circle. And at a point here, we would differentiate in this direction, which would basically be differentiating using the r direction, and the other direction is the theta is this direction, but when you do it, you'd have to use arc length. So here the variable would be r. You would take d by dr. But here you'd have to take d by ds with respect to arc length to get that direction and equate those. When you equate those, you would get the polar Cauchy-Riemann equations. So that's what the book is giving you a hint about. Anyway, that's worth knowing, I think. Questions about that? That's maybe the most involved question on the homework, but it's something good to think about. Let's see, I kind of wanted to do something fun today. Here's a fantastic thing. I'm shifting gears now. A fantastic thing about the complex exponential. And log. Okay, when you're talking about elementary functions in the real sense, so when you have real elementary functions, there's an entire zoo of elementary functions. Okay, let me list a few. You'd have e to the x, the natural log of x, sine of x, cosine of x, tangent of x, hyperbolic sine of x, hyperbolic cosine of x, etc., inverse hyperbolic cosine of x, inverse sine of x, square root of x, nth root of x, and basic algebraic functions. Those are, and if you combine all those things in all possible ways, you get what are called the elementary functions. There's a famous theorem, Liouville's theorem. E to the minus x squared dx cannot be expressed in terms of elementary functions. And you wonder how in the heck did Liouville figure that out so long ago? Which is a bummer because everybody wants to get their hands on that function. You can compute it numerically and be perfectly... Well, Liouville used complex analysis to demonstrate that. So I claim that the zoo is only two animals in the complex plane. The zoo of elementary functions is only two animals. Namely, e to the z and the complex log. And to show you, for example, I'll do an example. Let's do the inverse cosine function. Let's write z, here's an example, equals the inverse cosine of w. Okay, what would that would mean that cosine of z equals w. Or let me write it on this side. W equals cosine of z. And cosine of z is e to the iz plus e to the minus iz divided by 2. Okay, so now I'm going to do some algebra here. Let's, I'll multiply it by 2 by 2. I get 2w equals e to the iz plus e to the minus iz. And now I'm going to multiply by e to the plus iz, this equation. When I do that, I get 2w times e to the iz equals e to the iz squared plus 1. And I really realized this is a quadratic equation in the e to the iz. So I get 0 equals e to the iz squared minus 2 times w e to the iz plus 1. That's a quadratic equation. It's quadratic in and so now I can solve for e to the iz and see that e to the iz, using the quadratic formula, let's see, it would be minus b, that would be plus 2w, plus or minus, well, I have to think about square roots in the complex, so I'll use a square root to mean a complex square root. There'd be 2 of them, plus and minus 1. B squared would be minus 2w squared minus 4ac. That would be minus 4 over 2a. Funny, you get, when you mess around with that, I'll put a plus or minus here. There's 2 complex square roots of any number. This would be w plus or minus the square root. I can put that 2 inside the square root, and I'd get w squared minus 1. And so iz, I'm not going to think about what branches I have here, would be a log of w. Yeah, so when I think about which square root, I'm not going to think about that right now. There'd be there's 2 square roots, and I'm going to put plus here. I'll make that a red plus sign. There's 2 square roots. 2 complex square roots. So I don't know which one I would have to pick. Anyway, I've just expressed the complex inverse cosine function in terms of, let's see, 1 over I is minus I. So this would be minus I log if I was going to tell you what this really is, I'd have to think about what's the branch of log I'd have to use, and I'd have to think about which square root I'd have to take. But I've expressed the complex inverse cosine function. By the way, I do that by drawing pictures like I always do to figure out where the heck in the complex plane I am. This is the inverse cosine of w. And you can do that with all of those functions. The inverse hyperbolic sine, et cetera, they can all be expressed in terms of exponentials and log functions. And that observation allowed Liouville to go into the complex domain to solve that famous problem about not being able to find elementary functions to solve basic integrals. So on the way to Liouville's theorem, the elementary functions in C when you let go into the complex domain, the elementary functions are, fancy word, generated, meaning you compose them together over and over again by simply e to the z and its inverse and the algebraic functions, meaning things like you get in the quadratic formula with square roots. Of course, they get more complicated for higher order polynomials. That's cool. And in fact, his proof was fairly, if I had to teach it to you in a couple of weeks, I could. It's using basic facts about complex analysis. It's just you have to think kind of hard about it. And we don't want to think that hard. We want to get more tools under our belt before we start thinking about philosophical questions. Let's see. Yeah, it's a fun game to think about all those functions and how you would play around. It's quadratic formula, basically, getting all the equations for all the basic functions in terms of exponentials and logs. Of course, I didn't mention, what's another one to mention here? The complex cosine function is e to the iz plus e to the minus iz over 2. The complex sine function is e to the iz minus e to the minus iz over 2I. The complex tangent function would be the quotient of those two, which you could stick in terms of exponentials. Oh, I know what the tangent is. Etc. So those would be expressed in terms of exponentials. The inverse ones would require log functions. But that's all they require. Any last minute questions about anything? Well, don't get too carried away with that question about polar coordinates. It's just something I wanted you to think about. It's worth thinking about. I guess the main question for that problem would be to figure out you want those derivatives in those directions to be with respect to the distance function, which would be in the radial direction it's just r. In the tangent direction there, you have to be careful to differentiate with respect to s. That's where the 1 over r's come from, the arc length of that thing, so that it's related to the actual difference quotient. So, and that's just a little bit of calculus. It's worth sort of thinking about it. I think I'm kind of out of time now. But any last minute questions about anything? Yeah.
How do you, for the quadratic part, why can't you just remove the minus?
In the square root?
Yeah.
No, so that symbol means a complex square root. And there's two complex square roots. When we're dealing with real numbers, and that'd be a real thing, and it'd be a plus or minus something I, or a plus or minus something. In the complex domain, the roots would also be plus or minus. They just wouldn't be, they'd be...
So I guess they kind of cancel out?
No, they don't cancel out. I mean, I have to pick a root. I have to pick the right root when I do that.
Okay. So it's just an arbitrary choice?
Yeah, it's a choice between they would be plus and minus each other. So, yeah.